Hello everyone, this is Marco Riani speaking.
And I am Anthony Atkinson.
With this video, we'd like to talk about section 8.4 of our book, Heteroskedasticity.
We are concerned with heteroskedastic regression models. We have already had several methods in our book of dealing with data which are not homoskedastic. For example, the Box-Cox transformation, where there is the relationship between the mean and the variance. Finding the proper transformation parameter gets rid of the heteroskedasticity, and ordinary least squares can be applied to the observations. We also, much more briefly, discussed the transformation of both sides of a regression model. This is a way of transforming to get heteroskedasticity whilst maintaining the relationship between y and a linear model. If neither of these is possible, the heteroskedasticity is not clearly related to the values of the mean. We therefore use some form of weighted regression.
In our book, we often deal with international trade data. That is, data which have on the x-axis the quantity and on the y-axis the value. And these data are intrinsically heteroskedastic in the sense that for a very, very small quantity, the value is very close to zero. On the other end, if the quantity is large, the range of the value is certainly much greater.
It is these kind of data that we wish to analyze. We need not only to analyze the data, but to come up with a system of analysis which is based on regression and which is amenable to the forward search. So here are the models for non-constant variance which we use with the forward search. The idea is that we have a parametric form for the variance, and we have to analyze the parameters in the variance function as well as estimating the parameters in the linear model for the response. So we have to estimate not only the beta parameter in the linear model, but we also have to estimate any parameters that there are in the way in which we parameterize the variance. Equation 819 gives the variance function, sigma squared I for the ith observation, that's the variance of yi, and it is sigma squared, which will have to be estimated, and then multiplied by 1 plus the exponential of a linear model. So we have also to estimate the parameters gamma. This form is used, for example, in the analysis of pharmacokinetic data, and we analyze the properties of this model in a paper by three of the authors, Atkinson, Riani, and Torti. We therefore denote this model by ART. In our examples, the variables x and z are identical, but they do not have to be. However, all elements of the two-parameter vectors are distinct. In consequence, the information matrix is block diagonal. For given gamma, estimation of beta is by weighted least squares, and sigma squared is estimated from the residual sum of squares. For a given value of gamma, the weights are defined as wi, that's sigma squared over sigma squared I, which is some function g of the linear model. It is convenient numerically to rewrite this in a weighted form. So we can write yiw is the square root of wi times yi, and xiw is the square root of wi times xi, and w is an n by n diagonal matrix. Then we just have to find the parameters beta given gamma. We have a weighted regression model of the form given below. It remains to estimate gamma numerical maximization of the likelihood is one possibility. However, since we need to estimate the parameters for each subset of the data in the forward search, of which there are almost n, Atkinson, Riani and Todorov use a more efficient scoring algorithm. An important property of this model is that provided sigma squared is greater than 0, the variance does not approach 0 as the Zi go to 0. A simpler model for heteroskedasticity with a skedastic equation in which there is no value of 1, so sigma squared I is just sigma squared times an exponential, was introduced by Harvey. We denote this by HAR. We will compare these two methods in one of our examples.
So the first example that we consider is a dataset which refers to imports from Switzerland to Italy, and this is the code. If you want to know more about this code, you can search this code and then in internet, and then this refers to newsprint rolls sheets greater than 28 centimeters. So this is one of the thousands of datasets that are routinely examined by the Joint Research Center of the European Commission with the purpose of detecting atypical observations. This is the scatter plot of this data. On the x-axis we have the weight, on the y-axis we have the value.
Well, we certainly see a general trend of heteroskedasticity, although it might partly be caused, we shall find out whether it is or not, by the far greater number of observations with an x value around 0.8 than are around, say, 0.1. But there also seem to be some observations in this more dense region lying above what is otherwise a pretty good line, and also a few lying below. We are interested then in estimation of heteroskedasticity under contamination. That is, we need to use a robust method.
So we want to know, for example, what is the effect of this group of units on parameter estimates, what is the effect of these outliers, and then we want to know whether these units can be considered as atypical or not. Clearly, this is an example with just one explanatory variable, but the point is that you want to answer this question also in cases where you have several explanatory variables. And in the case of the Joint Research Center, the number of datasets which is used is really overwhelming. So you must have automatic methods which point out the presence of atypical observations. In our code we specify the kind of heteroskedasticity, and then we have the routine which computes the monitoring of parameter estimates. Then we go to the plot.
Figure 8.13 shows monitoring plot when we used the model ART for heteroskedasticity. We can see that most of the searches, both the alpha parameter and log theta as a numerically convenient transformation of gamma, oscillate around a sort of horizontal way, but suddenly, at the very end of the search, we see that both parameters drop sharply. The estimate of sigma squared, on the other hand, increases, as is often the case in regression models, gently with the value of m, but finally here, it suddenly again increases at the very end.
Now we move to the monitoring of residuals, and then we create figure 8.14.
The statistical analysis in figure 8.14 shows the monitoring plot of the scaled residuals in the scale space of weighted y and weighted x. The plot is very stable over most of the forward search, showing the two extreme outliers for low values of x that are a feature of figure 8.12.
Here you can see the effect of the introduction of the last two units. And if you want to have additional information about this trajectory, there is an option which is data tooltip that enables you to have information about a particular unit when it entered the search and the unit name. Finally, we can see group of units with large constant negative residuals in the bottom part of the plot. The one that we have just done is an exploratory data analysis. Now we want to run the automatic procedure for outlier detection, and in this case it detects 38 outliers.
Using the 99% bonfirized confidence bands.
We can specify option plot is equal to 1 in order to be able to see the outliers that are found. In this case, 38 outliers. So you can see here the original scatter of y against our explanatory variables with the outliers that have been detected and marked in red color. This group that is below the bulk of the data could be seen clearly, but notice also that here there is a set of units that works with a price that is different from that of the other observations. Finally, there are these outlying units that have a combination of x and y, which is absolutely very far from that of the other observations. Note that in this case these units are not detected as outliers.
Because the parametric function we have used for the weights does not go to 0 as x1 goes to 0.
In the exercises we suggest to repeat the analysis using the other type of heteroskedasticity due to Harvey.
What do you think?
Now we do repeat the previous plots, but now with the bands. This is figure 8.15.
Perhaps the most important non-data analytical property is you can see that there's still quite a wide band at x, the weight, equal to 0. All the outliers that we have been discussing have fallen outside the bands, and none of them fall inside the bands, and no observations that have been declared to be normal lie outside the bands. So the forward search and these bands provide a clear dichotomic classification of the data into acceptable main units and outliers.
Now we move to our second international trade example, and this is referred to this Tariq code.
This code refers to mollusks. However, this covers quite a variety of shellfish, and we can expect that the data will not be highly homogeneous.
We start showing the scatter plot of the data.
There are 1,302 observations. The scatter plot of the data in figure 8.16 shows that the general form of the set of data is quite different from that for the international trade data that we have been previously looking at. There, the highest density of observations was from scaled weights of 0.65 to 1. Here, there is a concentration of observations near the origin, fanning out strongly and clearly showing heteroskedasticity. There is a central line in this scatter, which gives rise to leverage points, and there is a line of points near to the bottom of the fan of observations, which may be outlying. There are also some seemingly too large values at low values of x.
Now we do a forward search, and then we see the monitoring plot of residuals. Monitoring plot of scale residuals shows a clear group of units having very large residuals, and the fact that this is a group of units lying in the same portion of the space is clearly seen, but the fact that they react in the same way to the introduction of the most atypical units. Now, if we want to see these units, we brush them and then we see their position in the y-x plot.
When we plot the highlighted units in the scatter plot of the data, we see that the location of these extreme observations, 5, are at very low values of x, and so are unlikely to be important in the detection of financial irregularity. The other 2 outliers are, as we have seen before, clear of the main body of the data. It appears that these 7 outliers come from a different regression line. The next stage in any investigation would be to check whether they all come from the same country. If the answer is positive, the data for preceding and subsequent years should be checked. We conclude this introduction to the use of the forward search in the analysis of heteroskedastic regression data by comparing the results from use of the skedastic relationship HAR and ART.
This is the confidence bands which come out from using the HAR heteroskedasticity. Note, if we zoom, that there is a unit which is also detected as outlier, and in fact this form of heteroskedasticity has a variance which goes to 0 as x goes to 0, therefore here it tends to detect even small slight deviation from
values of y close to 0. If we now compare this with the use of ART,
we can see now that the width of the band does not go to 0 as x goes to 0.
We thus avoid indicating outliers that are of very little economic importance.
In the exercises, you can find additional examples for the analysis of heteroskedastic data, and let us come to the conclusion for the heteroskedastic analysis.
Our analysis has shown not only interesting features of the data, but how we can extend the monitoring provided by the forward search to heteroskedastic regression.
Then we have also discussed the 2 forms of parameterizing the heteroskedasticity, and we discussed their implications.
Thank you very much for your attention, and arrivederci.
Ciao, arrivederci.